Thank you. Bye. Love you, bye. Hey, Jordan. All right, you're the first one on. We're still waiting on the girls, so we're going to give them a second. There's Emily. Hey, Emily.
Hi. Can you hear me?
I can hear you, yes.
Camera doesn't seem to be working.
All right, that's fine. You don't need your camera. I'll hold up my stuff if we need to check anything, and so you can check your work. I just won't be able to see what you write. But this section isn't really. We're not going to be drawing as much in this section of the Lewis structures. It's actually a really easy section, and I kind of skim over most of it because it's not as important. So I think that without the camera, you'll be fine. Emily, I think you don't have your mic on, though. I think it does have the slash through it now. And that's fine. You can type in the chat, and that's okay, too. So just type something in to let me know you're hearing me. Okay, that's fine. And although I could hear you the first time, it was really staticky, so it may just work to have you just type. That would be fine for today. So we are just missing Emily Mongold. I know! Snow days! What's up with this? Like, the biggest thing for me is yesterday. I know. What day is it today? Thursday? Yesterday was Wednesday, and GCA and a bunch of public schools were closed. Thank you. Hi. There we go. Yeah, but there was no snow until like after school would have normally been out. So I was going as a teacher. I wanted to have school. Why didn't we have school? There was no snow on the ground until like 3 in the afternoon or something, you know? So it was frustrating for me because now we have 2 more snow days on top of already having a week's worth of snow days.
Mom, the camera's on now. Oh, okay. Sorry. I was freaking.
You're fine. All right, so I'm going to try to text the Mongolds and just see if they're joining because they are late.
Okay.
All right, let's see. All right, so did you guys watch 8.5 video?
No.
Well, officially we weren't supposed to do this today. We were supposed to do our lab. So did you read your lab directions?
I did do that. I read all of them, and I've been working on some of the, data table stuff that I can do now.
Good. So you should be working on writing the names down. After you should have already done the pre-lab questions. I don't think there were that many. I think there were like 3.
I did them well. Kind of was confused, but I'll probably be able to do them better. Like.
All right. So we'll have to do that lab on next week, and we'll have to discuss whether we would like to, how we'd like to handle that. So we'll wait until Emily Mongold's here as well, and we will all together discuss the schedule of next week, because next week we're going to have to do a lab and a review day, and then your test will be the following week. So that's going to be it.
So is today going to be like what we would have done on Tuesday?
Yes. So today, because we can't meet together to do our lab, we're going to essentially do the lesson that I would have taught you on Tuesday of next week, which is why it's okay that you haven't watched 8.5 yet, but you do still need to watch 8.5 and read the section 8.5. So make sure you guys are taking care of that. Yeah. I'm going to start because it's 5 minutes after, and I don't want to waste your guys' time, so we're going to start.
Are they coming or?
I haven't heard back yet. I don't know. Not really sure, but they should be. They know that we were going to meet at 12:30. They said that sounded fine. So we'll see. But we're going to go ahead and get started. And I think that the last time we did video lesson, I think I did forget to pray because we weren't in person. So I am going to say let's pray. We'll just pray over the camera, which is a little weird, but hey, it still works. So let's go ahead and pray. Do you guys have any prayer requests right now?
Nope.
Jordan does?
Wedding.
I guess that me and my mom don't go into the weather again.
Okay, so pray that you guys get healthy again and stay healthy.
Oh yeah, we could using the word weather reminded me that it would be nice to not have any more snow days.
It would be nice to not have any more snow days. I agree. There's supposedly another snowstorm coming though, so that may happen in another week.
Well, not pray. I don't have any faith.
But we'll pray that God will be merciful and then we will be able to meet in person again and not have to have these snow days. So let's go ahead and pray. Dearest Heavenly Father. Wow, that's mercy. Sorry, hang on. Hi, Mrs. Mongold. Hi, Emily. Okay, so are you using the link that I sent you guys in the text? Oh, hang on. I don't know why that would be. Maybe it's James said that I was able to start this broadcast without you guys all being in here, so it shouldn't be that. Let me just invite you again, I guess. I will send you another code. It's okay. Well, we are on, it's labeled Church Chemistry and 11818.
No, I just think it's weird to have it as, you know?
Church Chemistry 11818. Oh, you can? All right. And you're clicking on it and putting in the code, or? Sorry, Emily Mongold's trying to get on. She can't join. All right, hang on. Let me see if I can send you another message. All right. If not, I'm gonna have to call James because I don't know. I'm not a technical person. He is, so I'll have to ask him for help. Sorry.
Janet.
Yes, ma'am.
Tell her to check her email. It worked last time when I sent it to her by email, and I'm sending it to her by email.
Are you still there? Okay. Check your email. Because, yes. Well, she said that she's sending you one now, and that it worked last time she sent you via email, so she's sending it again. Just check there and try that link. No, it's fine. We might have Emily Mongold soon. Let's see. It's okay. We were just about to pray. We were going over a few like technical things and trying to stall and wait for you. And then I was like, okay, we're gonna start. All right. All right. See you in a second. Bye. All right. Apparently it's working. She's right here.
Hi.
Hi, Emily. Everybody say hi. Your sound is off and your film, the camera is off, Emily. So if you want to be able to see us, you got to turn it back on.
Okay, I think it's.
Yay! There's Emily.
Hi.
You were praying. Did you have any other prayer requests?
Hi.
All right, never mind. I'll just start. Dear Heavenly Father, thank you so much that we were able to figure the technical things out and get everybody in class today. We pray that you would just help this to be an effective time where everything makes sense and that I'm able to just really clearly present the material. I pray that you just be with everyone in the snow days, that they be safe. I know James is out working and probably several other people. I pray that you just really would go before them and keep them safe. I pray this all in Jesus' name. Amen. All right, guys. So I doubt that you have watched the video, Emily 8.5, because the other two haven't,
No.
and that's okay. Because today
Sorry.
we're technically supposed to be doing a lab, and that's okay. We'll do the lab next week, probably Tuesday or Thursday. We have to talk about that still at the end of the lesson and see what your parents think and see what you guys think as far as which day we want to meet in person for that lab. The other day, whichever day we choose, the other day will be a review day for your test that's going to come up the week after. And that test will be on Tuesday. So everybody mark your calendars. Not this next Tuesday, but the following Tuesday will be our test. So it'll be on, let me see my calendar. It'll be on the 29th of January. January 29th is going to be our test. So we will decide whether we want to meet in person on Thursday, which I think would be better because CEF is on Thursdays and you guys do CEF. So I think that that would be the best option. And I think that Tuesday we should do another video lesson where we are just reviewing and I'm answering questions and you guys have a chance to really practice the material of the whole chapter. But I mean, I guess we can vote now. Do you guys think that you would like to meet on Tuesday via video and do the review day on Tuesday and then do the lab on Thursday? Would that be?
I like that.
Yeah? That would work. All right. And Jordan, would Thursday work for the lab and Tuesday for the review day? Yeah?
That'd be fun.
All right. So that's decided. We're going to meet on Thursday next week for our lab. We're going to meet on Tuesday of next week for our review, and that's going to be a video session. So we'll do it just like this today. And that will be fun. So for today, you guys, your homework after this is done, you're going to obviously have to read this section 8.5, and you're going to have to watch the video for 8.5. I will think of some practice problems as well, and I will give you those before we finish, but I have to decide that still because I have to see what we get through right now. So let's go ahead and just start with the chapter, and I want everybody to be on 265 in their textbook, page 265. Electronegativity and polarity. So, what were the 4 trends that we learned about? Chapter 6, I think, and we wrote a paper about that. There are 4 trends on how the periodic table works, and you went across the top and down the side of the periodic table.
There's ionic radius and atomic radius and electronic activity and
Ionization.
yes, of course.
Energy. Great job. All right, so we have those 4 trends. And remember, the ionic radius and the atomic radius relate to each other. And as you go down the periodic table in a group, they get larger. The radius will get larger because the atom is getting bigger, so it's going to take up, you know, a larger radius. But as you go across the top, the radius ones, they decrease as you go across the, you know, across a row. Whereas electronegativity and ionization energy were the exact opposite. As you went across the row, they got larger, and as you went down the column, they got smaller. So remember that this is the ability of an atom to pretty much to steal from another atom, to take an electron. So where do you think are going to be the most, what is the most electronegative atom ever? It's the one that's going to steal the most electrons, most atoms to start.
Like-
Where is it or what is it?
What is it? Do you know? The particular element.
Nothing we don't.
You can look on page 265. Remember that it's going to be the highest at the top and at the corner.
Helium?
Helium is the wrong corner. Other corner.
Hydrogen. Hydrogen.
Hydrogen is the wrong corner. Wait, no, hydrogen is noble gas. Don't count the noble gases, but you're really close.
I don't have my
Lithium.
Fluorine?
Fluorine.
fluorine.
Fluorine. Look, you have a table. It's on page 265. I want you to look at the actual numbers that are on that table. Which number is the biggest? Like, compare a few things. You got some that are like 0.7, some that are 0.82. What is
Oh,
fluorine?
chlorine. Chlorine, right?
No, hang on. Let me type it. Fluor with an F.
Oh, fluorine. Okay.
Fluorine.
Okay.
So notice fluorine's number is 3.98. That's its electronegativity number. These values were actually measured. They're not guesses. They are really measured, and they're written down based on how likely an atom is to steal an electron. And fluorine is the king. He is the most electronegative. He will steal the most times. And notice that oxygen and chlorine are right there near it with 3.44 and 3.16, and then nitrogen with 3.04. And as you go out and away from fluorine, you get smaller and smaller. But that's how electronegativity works. It's the highest in that top corner. Why did we not count things like helium or neon or other things like that? Why are those particular elements not counted? Jordan, I see that hand. Go ahead.
Because they're noble gases.
And what's different about a noble gas? Is a noble gas going to need to steal an electron?
No. They're-
Why not?
because they already have 8 valence electrons.
Good. They already are full. They already have 8 valence electrons, and so they do not need to take any electrons from anybody because they have as many as they need. So that is why you don't count those. You're going to start with the halogens. Those are going to be your starting point in the electronegativity. So the first whole page of this is going to be talking about the octet rule and why things want to steal electrons to become stable. And then it's going to talk about electronegativity. So we already know that trend, and I feel that you guys, we've covered it in both the last 2 chapters, and we're reminding ourselves again here about why electronegativity matters and that needing to have 8 electrons is important, okay? So that's really what that trend is talking about, but it's kind of fun to see how electronegativity actually impacts a real molecule. So if you turn the page, you're going to see how the difference in the electronegativity values is going to matter. So notice that you have different types of bond character. And you notice on 8.7, the table 8.7 at the top of page 266, it's going to talk about whether something is classified as ionic or polar covalent or mostly covalent or non-polar covalent. Do you see that table with those 4 distinctions?
Yes.
Notice how there's a range of values, whether it's 0 or less than 0.4, or between 0.4 and 1.7, and greater than 1.7, right?
Mhm.
What you're going to have to do to find out if something is one of these categories is subtract the 2 electronegativity values and see what range you fall under. So let's go ahead and practice this. You know something that's ionic? It's going to have a what and a what bonded together. What type of
Metal.
metal and
Non.
non-metal? Good. So we have a metal and a non-metal. Choose 2 of those for me. Give me a metal and give me any non-metal.
Lead. The metal.
Oxygen.
All right, lead and oxygen. So we got PB. PB, what is its electronegativity value, please?
Yeah.
It's element 82. It's in blue. It's all the way at the
So that
bottom.
would be 1.8.
1.8. And then where's oxygen?
Mine's just 207.
Lead? Yours?
Oxygen. Oxygen 3.44.
Oxygen is 3.44. Emily, you must be looking the wrong element. Do you see PB?
What page is this on?
What?
What page is this on?
On page 265.
1.8. That's right. One right next to it is 1.8 too.
Yeah. All right, so now notice what we do with those two values. We're going to subtract the two. And because we don't want a negative number, let's just subtract 3.44 minus 1.8. Notice what you get? 1.64.
Okay.
Now go over and check your range. Where does that fall on the categories?
It would be polar covalent.
Oh, because we chose one so close to the non-metals. Yes, it is. I would still consider it mostly ionic because it's so close, and it's a non-metal and a metal. But because it is so close, that's why it's kind of flirting with that line there.
Yeah, because it says for mostly ionic. I was about to say that, but it says that it would be greater
Yes.
than 7, but this isn't greater.
Yeah, it's not greater. So that was a bad example, but look, look at where it is on the periodic table. It's not like most metals, which are over here. It's like really close to these non-metals and metalloids, right? That's why it's so close to being polar, all right? So let's try a better example. Let's get a metal that we know is like a solid metal, like
Copper?
copper would work. All right, so copper is 1.90.
Just do oxygen again.
Yeah, let's do oxygen again. So 3.44.
Minus 1.90 or 1.9, whichever.
This isn't going to work out so well. This is still 1.54.
Yeah, I see 1.54 too.
Let's try.
I'm choosing the metal this time. No more you guys choosing it. Choose rubidium or potassium. I don't care which, but let's choose one of those two.
Is
Like-
rubidium RB?
Yes, it is. 0.82. All right, and then 3.44 for oxygen. Because that's like a alkali metal. So those are like for sure going to treat us the way that we want them to. So we've got 3.44 minus 0.82. That's 2.62. And what would we label this as?
Ah,
Ionic. Mostly ionic.
Mostly ionic. Good. So the difference is what's going to help us with that range. Now, what we're going to look at is something that would be considered, let's go with phosphorus and fluorine. Classify that bond for me. So take phosphorus and chlorine, and based on the range that you get, tell me whether it is mostly ionic, polar covalent, mostly covalent, or nonpolar. So just figure that one out for me. Fluorine is 3.98, and phosphorus is 2.49.
Phosphorus and what?
Phosphorus and fluorine. So fluorine, yeah, element 9 and element 15.
would it be polar covalent because I have 0.97?
Do you have? Oh, I have fluorine 3.98.
I have 1.25.
3.98.
3.98 minus 2.19. 3.98 minus 2.19.
I have 1.25 for mine.
Yeah, I did the wrong thing.
I got 1.79. But I don't.
I used the computer. How did I get that? Okay.
Fluorine and phosphorus.
1.79.
You guys see that now? Fluorine and phosphorus.
Oh, wait. Wait, wrong.
Is that everybody on the same page as me?
Yes, ma'am.
All right. I'm going to just start writing down the letters that I talk about for the elements because apparently it's not really coming out as clearly over the video, and you guys are finding the wrong elements, I think. So, with this in mind, 1.79, where is that range?
Mostly ionic.
So, I'm going to give you one more. Let's talk about if we had oxygen, O2. And yes, this is a trick question. Find the values for O2, oxygen. So you're going to find the value for oxygen and
Covalent.
oxygen. So you're going to go So you have to take the value for oxygen and subtract the value for oxygen.
Non-polar covalent.
Non-polar covalent.
Because, you know, it's 0. So that's how you can tell the range for that one. Let me see. I would like to give you guys the names. All right. So we have whether something's non-polar or polar, but we didn't really talk about what that means. What's the difference between an ionic bond and a covalent bond as far as how you treat the electrons?
I'm being completely quiet. I have no idea what's going on.
Sorry.
Really...
I'm transitioning. I'm trying to help you figure out what polar and non-polar means. What does an ionic bond do with an electron? Go ahead, Jordan.
With an ionic bond, you're taking electrons from another element.
Good.
Oh, from your atom.
So if this is fluorine and this is chlorine, not a good example. Fluorine and sodium. If this is sodium. Fluorine's going to come and go, I need that. Thank you. Mine now. Right? It steals it. What does a covalent bond do?
Share.
They share.
They share. So these would be like two atoms. It could be fluorine and hydrogen, fluorine and carbon, whatever. They go, hey, I have an electron and I have an electron. Let's share them together between the two of us and we're all happy, right? But not always everyone's happy. Because in covalent bond, sometimes atoms are stronger than other atoms. So you know fluorine and hydrogen, let's say that that's what we're talking about and they're sharing. Fluorine is very, very strong, right? It's got a very high electronegativity. Hydrogen, it's got a, what's the number? Got a 2.2, but it's not as strong as fluorine is. So what's going to happen is the fluorine's going to go, he's going to hang out with me more often. Now it's still sharing them. It hasn't taken them completely. It's still sharing them, but more often the electrons are going to be over here by fluorine and not over here by hydrogen. Does that make sense?
Mm-hmm.
So that's an unequal sharing. So they're not actually sharing in the middle between, it's not, the electrons aren't spending equal time between both atoms. They're spending more time with fluorine and less time with hydrogen. That's when we have a polar covalent bond. Because a polar covalent bond is a bond where you have unequal sharing of those electrons, and so it imparts a partial negative charge on this atom and a partial positive charge on the other atom. Because this one doesn't get to have the electrons as often, so it's going to show its positive charge from its protons more than the other one will. This one has the electrons more often, and so it's going to have more of the negative charge on this side. So this imparts a partial charge of negative and positive, kind of like, what kind of a bond? What actually imparts a charge for good, forever, for always?
Healthy?
Like an ionic bond, because an ionic bond actually imparts a charge. Like, you remember when this happened, the atom took it, and this is permanently positive, a cation, and this is permanently negative, an anion. Well, it's not going to take it forever, but it's a partial charge. It is the same idea where you have a partial positive and a partial negative. The one with the electrons more often, that's the negative one. The one with electrons less often, that's the positive one. So far, does that make sense as why if the electrons are hanging out with one atom more often, that atom will be a little bit more negative, and it'll be a little bit more positive on the other atom?
Yeah.
Well, that's what we're doing with the subtracting. The actual table, you know how you have that range? When you subtract these electronegativity values, you're going to see if it's going to be sharing equally, which would be like oxygen. When O2 was bonding together, they shared equally. They never really, one wasn't stronger than the other because they're the same atom, and so they shared perfectly. They're going to be no charge at all. That doesn't always happen, though. Sometimes a charge is incurred because of the one atom holding the electrons more often. Okay? All right, so that's what you're going to use this table for. On your test next week, on the 29th, I am going to be giving you these values. You do not have to memorize the electronegativity numbers, okay? What you do have to know how to do is you need to know that you need to subtract the two numbers and check where it falls on the range, all right? So you'll need to know based on if it's a difference of less than 0.4, that it's mostly covalent. If it's a difference of 0.4 to 1.7, you'd have to know that it's polar covalent. Does that make sense?
Mm-hmm.
All right. So you'll have to rank it based on that. So you have to know that you need to subtract them, but I'll give you those numbers. I will also give you, because I'm nice, I will also give you the range. You don't have to memorize the chart. You just have to know how to categorize them on the chart.
Thank you. That's really nice.
You're welcome. It's not something that you have to memorize. It's just something that you're going to have to be able to go, oh yeah, I don't need to add these. I need to subtract them and find where they fall on this chart. Okay? All right. So that's a polar covalent bond versus a nonpolar. And now what we have to talk about is, oh, notice, look at page 267.
Mm-hmm.
The way that you show those when you have polar, notice that they have hydrogen and chlorine at the top, and they subtracted the values, and they ended up with a difference of 0.96, which means that this is what on the chart?
The polar covalent?
It is polar covalent. The way that they show that when they have the atoms, they draw a delta sign, and they say delta positive, delta negative, because they're going to tell you which side is going to have the electrons more often. By the way, I'm going to draw that for you. Actually, no. I have atoms. Here. All right. So this is HCl, hydrogen, chlorine, right? Which atom is going to have the electrons more of the time? Is it going to be the hydrogen or is it going to be the chlorine?
Chlorine?
Good. It is the chlorine. Tell me how you would know that.
Because it's bigger.
It's not because it's larger. What else could it be because of? Not
As
because,
well.
It has more electronic.
I said it
because
first.
it is the one that has the higher electronegativity. Good job, guys. That's why this one gets to be the one that holds the more electrons, because this is the one that has an electronegativity value of 3.16.
Okay.
Right? So it's the stronger of the two. So it's the one that's going to have the electrons more often. So when you show that, you use the symbol delta, which kind of looks like an and sign. Like this, like that, delta. And you're going to have a delta negative because this side is the side that holds the electrons more often, so it's going to be partially negative. So you show that with a delta negative. Does that make sense?
It's just like an S.
Kind of, yeah. You can look at your, it's kind of like
Okay, I see it.
that sign, kind of.
Mm-hmm.
I feel like this
And then
would
on the other
probably
side,
if we had watched the videos and read the pages.
yeah, this was on the video. Yes. Yes, all of this is on the video. So there's your delta positive on this side.
Okay.
So the delta is really just, I want you to be able to recognize the symbol. It kind of looks like an S or a figure 8. And it's what you distinguish positive or negative with. And you just say it as delta positive, delta negative. Okay?
Okay.
All right.
Someone's Toggle made up that sign.
It's actually Greek. It's Greek to me, right?
Okay.
It's really Greek. All right. So now what we need to look at is the when you have a molecule, because if you just have two atoms, it's pretty easy to tell if it's polar or nonpolar, right? But sometimes we have atoms that are different shapes. Remember, that's what we learned in 8.4 is different shapes that are like tetrahedral or polar, well, not polar, sorry, or bent or you know, trigonal pyramidal or trigonal bipyramidal. So now we have to figure out with the polarity of a molecule based on its shape, because that does impact whether it's going to express its polar nature or not. So turn the page. And you're going to look at the picture at the top, 268. All right, so polar molecules at the top. Different shapes are going to always be polar or not be polar. All right? So notice how you have your bent shape. All right, this is bent, right? Pretend that there's two bulby things at the top, but you don't really have to see them. They're the unpaired electrons up here. So this is a bond between oxygen and hydrogen. What I would like you to do is to actually find the values and subtract them for me and tell me what you get. Oxygen and hydrogen.
$1.24.
Good. There's a difference of 1.24 between these, which means it is polar. To see how that's the first step. Subtract the values. Second step, you check the shape because some shapes don't express their polar. So which one of these is going to be wanting to be more negative, the oxygen or the hydrogens?
The oxygen.
The oxygen because it's stronger. So this one is the one that's going to hold the electrons more often. So this is going to be where your partial negative is. These will be where your partial positive is. If this is interacting with the world, so here's something, an object outside. If it goes this way, what's it going to present to this? What
Positive.
charge? The positive charge. And so if this was a positive charge, they would repel, right? If this was a negative charge, they'd be attracted. What if it came at it like this?
It'd be negative.
It'd be negative. So if this was positive, it would be attracted. If this was negative, it would be repelling, right? So by the nature of the shape, the polar nature is able to be expressed and felt by the world, right? Now I want you to think about it. Which shape is this? Hang on, let me build it first. What shape is this? Four single bonds.
Tetrahedral.
Tetrahedral. All right. So let's pretend that this one is FH4. FH4. So this is 4 hydrogens and 1 fluorine. So take fluorine's value of 3.98 and subtract the hydrogen of 2.20. 1.78, right?
Yes.
That means it is polar, right? Is it going to express that polar nature to the outside world? Where does the negative charge want to be? The negative charge will be which one?
It says it's most.
To the center.
The center.
Yeah.
All right. If it's in the center, I'm sorry, FH3 would never, FH4 wouldn't be something that can form. Save that example. Save this number. This is actually not tetrahedral. This would be linear. That was my fault. I chose the wrong atom. Sorry. So this is what this looks like. The negative charge would want to be here, right?
Mm-hmm.
Positive charge would want to be here because it'd be 1F and 1H. So if this comes into something like an object here, it'll express the negative side, right? And if it comes this way, it'll express the positive side, right?
Mm-hmm.
So linear is also going to be able to express its polar nature. Bent was able to, linear was able to. Now let's go back to the tetrahedral, and we're going to have this be carbon, because carbon can have 4 things bond to it. CH4 instead, because that's a real thing in real life. So carbon is 2.55 minus the 2.20. We're going to end up with 3.35. Mostly covalent. Is this going to be polar just by the nature of the numbers?
Yes.
Mostly covalent means that they share equally, so no. Just by the numbers, do the math, it's not polar. I need to find one that is. Hang on, I'm trying to think of one that will be.
I'm really fascinated with this video.
I know it exists. There's a tetrahedral thing that would be polar, so let's just talk about it, and let's not try to choose an example, because I'm really bad at choosing random things that will actually have the numbers that they should be, apparently.
It's okay.
Apparently, I'm really bad at this. So, if this is an object that would have a polarity, right? So the negative charge would be the more electronegative thing in the center, and the positives would be on the outside. This is what I'm trying to get you to see is, when it comes in contact with the world, it's going to present one of this, and that'd be positive, right?
Mm-hmm.
But then if it came at this side, it also express a what?
Positive.
If it came at this side, it also express a,
Positive.
and if it came at this side, it would also express,
Positive.
would there ever be a time that it wouldn't express a positive charge?
No.
No.
Mm.
Because the positives are kind of cocooning, they're sheltering the negative charge, right? So the shape tetrahedral, even if you get, when you subtract the numbers, even if you get an electronegativity value that should be polar, if it's this shape, it's never going to express that. Because it's kind of like it shields. Like it bubbles, it cocoons the negative. All right? Does that make sense?
Yeah.
Okay, so to be called polar, you have to express two charges to the world, a positive and a negative. So if you are polar, but you only express the negative or the positive, like in this case, it's only expressing the positive, it can't be considered polar. So this shape, maybe you want to write that down, the tetrahedral shape will always express itself as being nonpolar. All right. Go back to where the shapes are, and you tell me what you think about which other shapes would behave like a tetrahedral would, where it shelters the charge.
Trigonal bipyramidal.
Yes. Trigonal bipyramidal and an octahedral. Both of those would cocoon their charge and shelter it, and it would only express whatever the outside atom was. So those ones would be, you know, just nonpolar shapes. All the other shapes could be polar. If when you do the subtraction, if you get a number that is considered polar, they would all the other shapes would work. Okay?
So trigonal pyramidal, trigonal bipyramidal, and octahedral.
Tetrahedral, trigonal bipyramidal, and octahedral. Technically, the trigonal pyramidal could still express it because, you know, you don't count that bulby top, the one where the lone pair of electrons is. So this top part would actually allow this part to be exposed to the world. So that's why it's only tetrahedral, trigonal bipyramidal, and octahedral. Those three shapes. All right. Questions? All right. So let's go back and see. All right, so solubility. To be soluble, this is a term you want to write down. To be soluble means you're able to be dissolved in. All right, or you're able to be dissolved by something.
Yeah.
So the physical property known as solubility is the ability of a substance to dissolve into another substance. Able to be dissolved. That's what we are saying. So if we talk about something going into water, water has positive and negative charges, right? So if we put salt, NaCl, into water, salt is an ionic bond. Where's the cation? Which one of those is the cation?
The Na.
The Na. The metal is the cation. So that's your positive. And your chlorine would be your
Negative.
Anion.
anion, your negative. So if you put that in water, let's just pretend that this is NaCl. So now this is going to be the sodium and that's going to be the chlorine. All right, so if you put this in water, what's the water molecule going to do to the salt?
Break it
Dissolve
apart.
it.
Break it apart. And it's going to take the negative, and which side of the water is going to try to face towards the negative?
The positive part.
The positive
Positive.
part, which are the hydrogens. It's surrounded like this on all sides. So there'd be like a million water molecules all around it, completely surrounding it, putting the hydrogens toward it. See?
And it'd be repelling the salt at the same time.
Good. And so then your positive, the cation, which part would be attracting that?
The
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 salt.
big part.
The oxygen. Boom. So it'd follow right like that and surround it like that until all of the salt was dissolved. The salt is considered soluble in water. If you take a covalent molecule, like a polar covalent molecule, and put it into water, it will also separate because there's partial positives and partial negatives. So it can be dissolved by water because it's got the positives and negatives. So some molecules that are covalent are able to be soluble and some are not, all right? Because some of them don't present positives. Like you have grease, like you're cleaning pots and pans, right? And you have a grease on your pot. if you just put water on it, it's technically going to just sit there. What do you need to put with the water?
The soap.
The soap. Because on its own, the grease is insoluble. It's not able to be dissolved by the water. There's no positives and negatives to attract it to the water. What does the dish soap do that helps make it possible for the water to take this grease away?
Adds positives and negatives.
It adds them. Okay, look. It's really simple. Here's the grease, right? Soap, as a molecule, has a side that's going to love water. That's called your hydrophilic side because it likes the water. Hydrophilic. It's going to have like a charge. And then it has a hydrophobic side, a side that hates water or fears water. And that side is actually going to be the one that attracts to the grease. And so it goes and stabs itself into the grease like that because it's attracted to it. And then the water comes by and it goes, hey, I like this guy. Hey, I'm going to try to take it with me. And guess what happens to the grease?
It gets lifted up.
It gets lifted up with it. Blooms. They go together. That's how soap works. It actually makes it so that the grease is able to be taken by the water because it puts a bunch of these little molecules all around the grease, and those are now attracted to the water. So that is how you make something that's insoluble maybe be soluble.
That's really cool.
Yay! I like hearing that. So, that's the way, like, Procter & Gamble and things like that, they hire chemists to do research to see how do we build more effective soaps? How do we get rid of stains and things like that the best? So, you can make a good living off of chemistry.
Seriously.
Right? All right, so now they're going to talk about intermolecular forces. And we already talked about these, I think, once before. We mentioned them briefly. There's going to be 3 of them. And you want to know them in order of strength. Who's the strongest, who's the weakest, right?
Mm-hmm.
So we're going to talk about those 3. There's going to be dispersion, dipole, and polar. I'm going to write those in for you.
I have no idea what's going on again.
Emily.
If we had studied.
Dispersion.
These are 3 types of intermolecular bonds. I have ranked them for you from weakest to strongest. So the weakest is your dispersion force. Strongest is your hydrogen bond.
Okay, wait. So hydrogen's at the top?
Hydrogen's the strongest. I've listed them weakest to strongest.
Okay.
Dipole? What?
Yes. Dipole. I will talk about it in a second. Oh, there should technically be a dash between the dipole. So it's dipole-dipole. All right. What does the prefix di mean?
2.
2. 2 poles. Dipole. So they say it twice. I don't know why. It's like saying hi. I don't know. Dipole. All right, so we're going to talk about these. The first one is dispersion. The important thing about dispersion is that it happens everywhere all the time between all atoms all over the place. What does it mean to disperse? If a police officer comes and says spread out, disperse, he means spread out, right? The electrons, we're going to go back to the parts of any atom. You have one in the center.
Nucleus.
Nucleus. What's inside the nucleus?
Protons and neutrons.
Protons and neutrons. What's on the outside in the cloud?
Electrons.
Electrons, and they're always zipping around, moving everywhere in their shapes, right? They're constantly moving. Well, with that constant motion, occasionally what's going to happen is on this atom, there's going to be a brief second, like less than a nanosecond, where the electrons at some point will maybe be clustered on this side more than on that side. What does that impart on this atom for just that briefest of second?
No.
A partial
Dispersion.
dispersion. Partial charge on this side. What kind of charge is this side? Because it's where all the electrons are.
Positive.
Electrons are what charge?
Positive.
Nope.
Negative.
Electrons are negative. So it's
Negative.
a partial negative charge here for a second. And then notice what's exposed over here. The protons. Because there's not as many electrons here. So what's going to have the charge here?
Positive.
partial positive. So notice how this atom that is neutral, for just the briefest of second, because the electrons are clustering to this side, are going to have a partial positive and a partial negative. Negative here, positive there, right?
That's polar, right?
That is dispersion. But it's going to last like that long because the electrons are going to keep moving, aren't they?
Mm-hmm.
But in that briefest of second, this atom has a neighbor atom right here, right? They're nearby, another atom. What do you think is going to happen to this atom's electrons while this one has this partial charge for a second? The electrons are also what charge?
Negative.
Negative. Are they going to want to hang out by a negative charge right here?
No.
No, so this one's electrons are going to shift to this side. And it's going to become partially negative on this side. And guess what? The atom that's next to it is going to
Move again.
move again. And so it just kind of is constantly rippling out like that. But it lasts like 2 seconds, and it's not very strong, but it happens everywhere, all the time. That's why we study it. But that's all we really need to know about it, is that it happens everywhere, that it's just the brief cluster of electrons for a fraction of a second longer than on this side and causing that partial charge, okay? That's dispersion.
And what did you call that? Intermolecular what?
Intermolecular bonds. Or, sorry, not bonds, forces. Intermolecular forces. There are 3 types of intermolecular forces. And that's the first one. All right, I have to go toss some bread in the oven, and I'm going to come right back.
Okay.
I'm just making fresh bread, and it's been rising, and it's about 10 minutes longer than it should have been rising, so I'm going to go put it in the oven, and I'll be right back.
Sounds good. So, Deanie.
Oh my goodness. I'm sorry. I'm studying right now. And I would suggest to be careful what you say because my mom's right behind the computer.
Doesn't
Hi,
it
Missy
pretty?
Flame.
Look at it. It's so
Oh, that's
pretty.
beautiful. That's
It's gonna make
beautiful bread.
bread.
I'm really hungry now. I love homemade bread.
Oh, I do too. It's really good. Aren't you gluten intolerant?
What does that have to do with anything?
I don't know.
It makes me sick and irritable, and I don't care.
That's funny. Hey guys.
I'm back. Okay. So, I'm so excited for when that finishes cooking. Sorry.
That looked good.
I love fresh bread.
Hmm.
I actually have 2 loaves like that, and then I have another loaf that's setting for 24 hours, and I'm going to make it tomorrow, and it's going to be artesian bread.
Oh, that's the best.
I really like making bread. Just
Mhm.
saying. I'll have to bring you guys some on Thursday. I'll bring you a fresh loaf that I make.
Oh, that'd be nice.
Have bread on top. Yeah, I'm maybe I'm weird, but I love baking.
Yeah, that's good.
I love eating, so we should be good friends.
All right, we got it. We'll work it out. I'll bring the bread, you bring the butter. All right, so what was dispersion we just talked about? There we go, dipole. And the one that you didn't, you were like, what? I'm gonna bring back my molecule, and this is for covalent things. Remember, the other one happened everywhere with any molecule anywhere. So ionic, covalent, metallic, wherever you are, that's going to happen, okay? This is specifically going to be for covalent things, and what's going to happen is it happens between polar covalent molecules. So remember, these are when you aren't sharing the electrons evenly, right? So if we're not sharing the electrons evenly, let's say we have this molecule, and this guy holds the electrons more often than this guy does. What was the charge, the partial charge on this atom? He's got more electrons more of the time.
So he's negative?
So he's partially negative. And then what's the charge on this guy?
Positive.
Positive. That's all.
That's it?
That's it. That's what a dipole is.
Oh, my.
I told you, it's not that hard. Dipole forces literally just happen between polar molecules. It's just when you have more electrons held on one side than the other. And so it's a partial negative and a partial positive. Now,
Another word for polar.
what?
It's another word for the polar.
Sort of, but, it's describing the force between them. Because watch, when we have let's say we have a liquid or a solid that is made up of polar molecules, like this, right? So we have a bunch of them. What's going to happen when these guys come together like this?
They're going to repel.
They're going to repel. And so where will they like to orient themselves? like maybe
Positive,
like that,
negative,
or
negative with
like that, or maybe like that, right? It doesn't matter as long as the negative is near the positive, right? That's going to affect the entire liquid because all of these molecules floating around, well, they've got like other molecules above them and below them, and they're always going to try to orient themselves as much as possible so that they're not like this. Instead, they're like this.
Mm-hmm.
So that spreads out throughout the entire liquid, and it affects how the liquid behaves because they're going to try to orient themselves as much as possible so that those partial positives and partial negatives will line up nicely. And because these ones would repel if they came near each other, they'd go, whoops, all right, now we're happy, right? That's actually what we're describing when we talk about dipole-dipole is the interaction between the molecules that are polar, like this. Are you ready for the last one?
Sure.
Hint. The name tells you something about it. What do you think what is it going to have to involve?
Hydrogen.
Water.
Ta-da! Jordan was right. Because it's a hydrogen bond. Now let me tell you this. Can we go back to a different math class? Ready? All squares are quadrilaterals. Right? What is a quadrilateral?
Polygon with 4 sides.
Yeah, it's a polygon with 4 sides, 2 sides that are parallel, and 2 sides that are parallel, right? That's all that it says. 2 sides parallel, 2 sides parallel. Are all parallelograms squares?
No.
No.
Because some could be what?
Rectangle.
Rectangles or diamonds or something else, right? That's what we're going to talk about today. All hydrogen bonds are dipole-dipole bonds. It's a specific type of dipole-dipole. Just like a quadrilateral, a square is a quadrilateral, right? Because that's a more broad category. Quadrilateral is more broad, square is more specific. We cannot say accurately that all quadrilaterals are squares. It's just that all squares must necessarily be quadrilaterals, right?
Mm-hmm.
Well, all hydrogen bonds are dipole-dipole bonds. Not all dipole-dipole bonds are hydrogen,
Okay.
right? Because a hydrogen bond is going to be between polar molecules. So that's why it is a dipole-dipole bond, because a dipole-dipole is just, the interaction between a polar molecule where you will line up, right, so that your positive is positive is with a negative, right? But with a hydrogen bond, you're more specific. It must be between a hydrogen atom and 3 elements. So write this down. The molecule that's working with this has to have hydrogen and one of these 3. It has to have either oxygen or fluorine or nitrogen.
Fluorine, nitrogen, oxygen.
And I'm going to type it. NOF. Say that for me.
What?
NOF.
NOF.
That's what we write down.
NOF. Have you guys ever seen Pinky and the Brain?
No.
Okay, well, it's a really old cartoon that I used to watch as a kid. And one of the mice was kind of crazy, and he would say "Narf" all the time.
Oh yeah.
And that's the sound I want you to think of when you think of hydrogen bonds. NOF. Because guess which 3 elements you have making this up?
Nitrogen, oxygen, and fluorine.
Nitrogen, oxygen, and fluorine. NOF. Right? So, water. Do we have hydrogen in one of those elements?
Yes.
Yes, we have hydrogens and oxygens. So, sorry, I have to think of another oxygen. There you go. There. So when you have water interacting with water, you're going to have the interaction between the positives, right, on the whites for the hydrogens, and the negatives on the oxygens, right? So when water molecules come together, if they come together like this, they're going to repel. And so they're going to try to orient themselves so that they're like that, right?
Mm-hmm.
Or so that they're like, it can be anything. It can be this, it can be this or this, whatever, as long as the positives are near the negative. That bond between this, so right here, the bond, right where that pen is, if you pretend that there's a dot, 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 that's an attractive force between the oxygen and the hydrogen on the other atom. That's a dipole-dipole bond, but it's more specifically a hydrogen bond because it's with hydrogen and the element oxygen.
Okay.
Or it could be between hydrogen and nitrogen, or hydrogen and fluorine. But in order to have these, like if this was fluorine and hydrogen, you could have hydrogen bonds.
So NOF is a stronger dipole-dipole bond.
Yes. NOF is a stronger type of dipole-dipole bond. Now, have you ever taken water and taken a penny and dripped your water on your penny slowly?
No.
Not on a pen.
I think I had to for physical science.
What happened when you did that?
I stayed on the penny.
Okay, and did it just stay on the, like, it didn't like splash?
It bubbled up.
It bubbled up,
Mhm.
right? That's because of the hydrogen bonds. It wouldn't happen if there weren't hydrogen bonds. This attraction is so strong that in those seconds it's overcoming gravity because gravity wants it to spill over, right? And it's going, no, I'm attracted to this oxygen right here. I'm attracted to my buddy. I'm not leaving him, right? We're attracted. We're bonded with a hydrogen bond. Now, this is not the same as the intermolecular bond that's the covalent bond holding this together, right? It's outside of that molecule, but it's between the two molecules. That's why they're called intermolecular bond, because inter means between instead of inside of. So it's the bond between the molecules. And that's very strong. Very, very strong. But even though it's very strong, it's still weaker than the covalent bond holding here. So your intramolecular bonds, the bonds that are inside, like ionic bonds and covalent bonds and metallic bonds, those are the strongest. You're never going to get stronger than that. But outside of that, when you're talking about between the molecules, the hydrogen bond is the strongest. So, preguntas? Questions?
No questions.
I
Okay.
don't think so.
Questions?
All right, turn the page then. We are not going to talk about forces and properties very much, and we are not necessarily going to dwell on covalent network solids. Just know that when you do have a covalent solid, you could have something like diamond, which is a very, very strong bond, or you could have something like graphite, which is really weak. It just depends on how the intermolecular bonds are being worked, okay? So we're not really going to focus on that, though, because it's not as important. So that really is all the information that I needed to convey to you guys. We will also have that information in the video that you're going to watch. But I really just kind of need to see if you have any questions, if it made sense.
Well, we won't know what to ask until after we watch the videos and read it and stuff.
Emily.
Well, then I guess you'll be out of luck. How about this? I'm going to have you guys practice some problems, and I'll stay on the camera while you practice a couple of them, and then we'll have you do a couple for homework. Okay?
Okay.
We'll test your knowledge. So we're going to do the 8.5 assessment. Let's see. All right, I'm going to have you guys, number 69 is describe a polar covalent bond. So when something is polar, describe what's happening. So go ahead and write that down really quick, and then I'll ask you to read what you have. Or you know what, better yet, just type it. Type it into the response, and each of you will type your own response. What is a polar covalent bond?
What? How can I write that down? Is
Okay, what do you guys, oh, Gotta wait until you're done typing, I guess.
I'm really bad at typing and thinking, so I have no idea.
All right, let's see.
I'm not done yet.
Oh,
That is more correct. Jordan, good job. So, Anne, wow. Okay, name. Emily. I've not done that all year, ever. Not yet. All right, Emily, tell me the difference between yours and Jordan's and why Jordan's is more accurate than yours. Learn from each other.
don't really see difference.
Okay, so yours, you were saying, is when they shift to one side of the molecule. That's what you're describing more as the temporary shift. That seems to be more like the dispersion force. Are you meaning that it's going to be held by one atom more of the time? Is that what you mean when you say shift?
Yeah, that's what I meant.
Got it. Okay, so it's just not coming across that way. So when you're typing, try to think of how to express it, that they're not shifting to one side, because that sounds more to me like how I would describe dispersion force, that they're shifting to one side temporarily. So maybe in your wording, you need to make sure that you say that they're not being shared equally. That's more clear with what you're trying to say, is the whole. So they are shifting to one side, but just say it's because they're not being shared equally, and I'll know that you're not talking about dispersion force. Okay? Unequal sharing, and there's a big difference between that. All right, good job. All right. So now, the ones that I decided, I read through all of these questions. The ones that I think that apply most to what you'll be expected to do is 74 through 77. That's only 4 questions. So what I'm going to do is have you do 74A. And then, what? Go ahead.
What page?
Oh, 270. The same page that you were working on.
Oh, got it. Okay.
All right. So 74A, and then we're going to do 75, but we're going to just do this, SCl2. We're going to start with those 2, and I want to see what you guys say before we go on, and I decide if I'm going to have you do more of this now or do it as homework.
Okay, so 74 we're doing A, and for right now we're doing 75 SCl2.
Yes.
Okay. S.
And I'm going to work it out too, so I can check to see where you guys, if you made a mistake, where it was. Let me see.
And what are we doing with this?
You're answering them. The first one is asking you to decide what type of bond. So is it going to be a polar bond? Is it going to be ionic? Is it going to be mostly polar or mostly covalent, or in, non-polar?
So if it says Cl2 and there's 2 of them, what do we do with that?
Just use the value from 1. So you're going to take the value of S and the value of Cl and still subtract.
I was setting it up like as a Lewis structure. I was not thinking.
Oh yeah, no, you're not doing a Lewis structure for this one.
So oh yeah. Okay.
Yes, yeah.
Jordan, the first one is correct. 74A, you got it right. And then same thing with 75. You got that one right as well, Jordan. So I think you know what you're doing. You're doing a good job. That is what I'm going to have you do on the test too, is I'll give you this situation where you have it, and Emily, good, that's 75, the S and Cl2, that's correct. When you subtract them, you get 0.58, and you have that labeled as polar covalent. So, that's how you're going to be seeing this, is that kind of question. When you did 74A, you just subtracted S and the H values to get 0.38, which was labeled mostly covalent. Emily, did you have enough time to practice these two, or?
I wasn't even sure which ones you want us to do right now. I got the SCl thing.
Okay. All right. So SCl2, what did you do with that? Tell me what you did.
I figured out that it's 158 difference, and that would make it mostly covalent. No.
Look at the chart. You're going to be given the chart on your thing. So it's greater than 0.4. So what would it be?
Mostly covalent, right?
Mostly covalent is less than. That's the symbol.
Polar covalent then.
Yes, so it's polar covalent. Good. All right.
And the other one was.
Oh, are we doing all of them right now?
No, just the two. One other thing, because since I see that you guys know how to do it, I'm going to have you do that, the rest of them as homework. So, I mean, you can start them right now if you want, and you get a jump start on your homework. That's fine. But I'm going to give you guys another one that I want to see you do it right now. It's going to be one where you draw a Lewis structure and then analyze the Lewis structure. So let's go ahead and look at that now.
Okay.
So go back to these. So I know that you guys can do 74, B, and C on your own. Then you're good. You can do those on your own. 75, you'll be able to do the other two on your own. I'm confident that you guys will know how to do those. 76 is just another example of the same thing. So what we're going to do is practice the newer thing of 77, where you draw the Lewis structure and then you analyze it. So you're going to subtract the values of the elements involved, and then you're going to see based on the shape, if the shape would allow it to be polar or non-polar, even with the values after you subtract. All right? So go ahead and do 77, only the SF4. SF4. So you're going to draw a Lewis structure first, and then you're going to subtract the values of the S and the F, and then you're going to see if the shape with the value, like, it could just be non-polar based on the subtraction. So, go through the steps and see if this molecule is polar or non-polar.
So we're just doing the regular Lewis dot structure, and
Yes,
then
regular Lewis dot structure. So that also practices the stuff we learned from 7th grade. That is, Jordan, they say on my answer key that you are missing one pair of electrons. So I want you to count those again from sulfur and fluorine. Let's see, fluorine would give you 7. 7 times 4 is going to be 28. And then let's see, what is the other one? Sulfur. Sulfur gives you 6, so 28 plus 6, and then divided by 2, and you're going to have 17 pairs. And when you count those, look at yours right now. You have 4 single bonds, so that's of your 17 pairs, you've used 4. And then on the outside edges, you used 1, 2, 3 at each fluorine, right? So
Right.
minus 3 times 4 minus 12. So you have one pair left. Where do you?
So I would have it on S.
Yes.
Can I show mine?
Put it on S. Yes, go ahead.
I was gonna move the camera. Can you see it?
I can. It just has to focus now. Hang on. Give it some time.
bless you.
Do you have
Hilarious.
chlorine in the center? No, you have sulfur. Okay, got it. Emily, you have 3 dots that don't belong there. The only thing that should be there is the sulfur and then 1 lone pair on the sulfur in the end.
I forgot to count. I forgot to count the lines, the bonds.
Oh yes, count those lines as well because those count. And Jordan, put the 2 dots together because if they're separated, they're not like a lone pair. They have to be right next to each other on the kitty corner. Perfect, Jordan. Good.
And then what kind of bond this is?
Yes. So now you have to look at subtracting the electronegativity values and see what that range that is, and then see if the shape, even if it would be polar, because I don't know, if it would be polar, you have to check if the shape would allow it to be polar. So, you know, quite a few steps.
Wow. All right, so I'm a little bit confused now. So I did the Lewis dot structure.
Okay, so let me check that first.
I don't know if you can
And
see it.
I think that I can see this clearly, but you have sulfur in the center, 4 lines off of sulfur attaching to the fluorines, and you have 3 double dots around each fluorine, right?
Yes.
And then in the center, you have 1 dot on sulfur.
Yes, because there's one extra. I didn't know where to put it. So
Good. You do put it on sulfur, but it's a 1 lone pair, so you have to show it just like you put the lone pairs on the fluorines, and you put 2 dots for the lone pairs. You have to put 2 dots on the sulfur to represent that last pair.
okay, so one extra dot, even though it's not.
All right, here's why, Emily. The line, straight line, that represents a double bond or a single bond, right? Where you're sharing 2 electrons, right? So you count those lines as 1 pair. Each of the dots on the fluorine, so you know how you have your F here? Like if you have F written right here and you put a dot, dot, and then dot, dot, and then dot, dot. Each of those double dots is a lone pair. It's not being shared with anybody, but it is a pair, so it's got to have 2 dots because it's showing 2 electrons.
Mhm.
So when you have 1 pair left over, you have to put that pair on sulfur. And again, because it's not a straight line, because it's not being shared, it's just being put on sulfur, you have to put it as 2 dots because it's, you know, 2 electrons in that pair.
Okay.
So the 1 dot would just represent 1 electron, and you actually have 2 because you have 1 pair. Just like if you have a pair of shoes on your feet, you have 2 shoes on your feet. So you have
Okay.
a pair of electrons left. That's what you're doing with the double dot.
Okay.
And you did everything else perfectly.
All right, and so from there,
So now you have to check and see, subtract the electronegativity values and figure out what you get. I still have to actually,
Yes.
let me see, I still have to subtract these values, so give me a second to subtract them and see what I get.
Okay.
That's 3.98 minus 3.58. All right, so I do end up with a difference of 1.4, which means that it would be polar, in the range of polar. But now let's look. It's not tetrahedral shape
It's not.
because you have a lone pair. Remember, tetrahedral, go back to that page, the tetrahedral would only have 4 single bonds. This has 4 single bonds and 1 lone pair.
5. But where did that go? I don't see that on the page. 5 with 1.
All right. So the way that it would look is it actually would look like the shape of the trigonal bipyramidal with the 3 in the center. Hang on. I'm just going to try to draw this to the best of my ability. You would have your center atom, and you'd have 3 off the center, and you'd have 1 going straight down, but then you'd have this bulby head. You see how you have like 3 in the center? Like this would be like angle 120. 120. So each of those, that makes a 120-degree angle. And then at the bottom, you'd have a 90-degree angle with an atom going down to here. And then you'd have at the top, instead of 1 atom joining the top because you don't have another atom, you have a lone pair. So this lone pair is right here. And so it is still technically a trigonal bipyramidal, but if it was a trigonal bipyramidal the way that it should have been with having another atom, it would have been nonpolar. But because this is just like this one.
So the tripyramidal?
Yeah, so it's trigonal bipyramidal, but just like the bent, where you, because of those lone pair electrons, you have access to your negative. This lone pair, like this one, means that you could have this negative right here. This charge could be exposed to the world through the top.
Uh-huh.
So it's actually going to be expressing its polar nature. So this actually is able to express its polar nature.
How are we supposed to memorize these shapes, though?
All right.
With 5 and 6, it's
All right. Well, we did talk about when we did this originally that the 5 and 6 could also include lone pairs. It's just how many things are on the center. Are there 5 things off of the center, or are there 6 things off the center? And so when we talked about, we could have 5 single bonds, right? Like it could be like XeCl5, right? Which would have 5 single bonds off of the center, right? Or it could be like this shape, SF4, which has
I wish they on the page that has
which has 4 single bonds off the center
Mhm.
and a lone pair. So we actually count it, like we're going to call that as having 5 things off the center. If it didn't have this lone pair, it would have been a tetrahedral, and you guys would have been right. But because it has the lone pair, it's considered the trigonal bipyramidal. But in this case, it's not really a full trigonal bipyramidal because it has a lone pair. So it is actually polar. So I know that I told you guys originally that trigonal bipyramidal and octahedral are just non-polar.
So it was a trick
They
question.
are.
Let me clarify. Just because I realized that what I said was a little misleading, okay? So if they're true trigonal bipyramidal and true octahedral where they have 5 of the same thing around the outside or 6 of the same thing around the outside, they can express their polar nature, okay? But if they have lone pairs involved, then that means that they would be able to be exposed, like there would be a piece of them that would be able to be exposed, all right? And so they could be polar if they have lone pairs. So let me just clarify what I said earlier. Those lone pairs make it so that if they do have those, they are okay, they're able to be exposed. I'm not going to try to trick you. So I'm not going to be trying to ask you ones with lone pairs as well. If I give you an octahedral shape, it's going to just be an octahedral shape, and it'll be nonpolar. All right? All right, so I'm not going to give you these exceptions like they're giving you, but you might as well practice some of them and see that it is true that it could happen this way, but I won't try to do that to you on your test. All right? All right, so I do think the next one, by the way, is not trying to trick you. It'll be a shape that you can recognize, and it'll be a shape that you can easily identify. It doesn't have any lone pairs on the next one. All right? So, so I think that we're done here. If you guys have any questions, you can ask them. But otherwise, I think that that's it. And I will see you guys on Tuesday. You should have, by Tuesday, answered the rest of these questions. So on Tuesday, when we start our class, I'm going to start by checking that you've completed questions 74 through 77.
Okay.
All right. And then we're going to review for your test. So we'll go through all of the sections on the chapter, and we'll get any questions, come with questions. So really just finish these questions, watch the video for 7.5, watch the video for 7, read the section for 8.5, and then we'll come ready to do our lab on Thursday. We'll do the review on Tuesday. That's it.
All right.
This on the next Tuesday. All right.
Thank you very much.
Bye.